Do you want to see the way I did the last homework?
You can work on it again. The answers are right.
Is it right?
Were they right? Or is this a different one than the one you had?
I solve for I3 and you cannot, the way I solve for I3, you have to solve for I2, plug it in and then get I3.
Yeah, you solved it differently. It's right. The way you solved it is right. I mean, you just did this step twice, adding them together. You just did it twice, right? Once.
Actually, this way gave me the wrong I3, so I solve for I2 and then solve for I2, I3, that's right. But, okay, so I solve for I2 and then I3.
You solve for I2. You solve for I2, right? Oh no, you solve for I3.
Yeah, that was wrong.
Oh, that was wrong?
Yeah.
Okay, so you solve for I2, they give you I2.
Yeah,
and then you plug the I2 inside an equation.
This one, and then I got I3. Yeah. So this I2 I plugged it in because after this step they ask you to find I2, and this I2 was wrong, and I had to use this one. Yeah?
Because you must find by negative sign, right?
Yeah.
So positive.
Huh. I don't know. So if they asked me to find I2, I have no idea.
No, it should be the same way that you might have just been mistake. What do you mean you have no idea what to do?
This I2 I plugged in and it was wrong. And that's the one I plugged in here to find I3, which is right.
Let me try to solve it.
And my number was off like 0.00 something again. When I used my number, I was wrong. When I used their answer to find the other number, it was right. Okay. Yeah.
yours?
What is?
I mean, is it the question on your account?
Yeah. Questions? Was I wrong again?
I'm not sure. I just got the numbers from your question, so I can redo it and see what's wrong. That's okay.
I have to find I2, and I find the total current and total resistance.
You have to find I2 when?
When it's closed.
When it's closed, after a long time or instantly?
I'm assuming it's after a long time.
Safe.
It is.
A long time after the switch is closed. Oh, Q fine. Get the charge. Charging the second capacitor after a long time. Switch is closed. What do you do?
The question here is, the switch is closed, Q2 panel is here.
Closed. Fine.
That's here, right?
Okay. C2. Charge on C2 after a long time after. Charge on C2 a long time after the switch is closed. So how much capacitor? How much charge will it be charged? How much charge will it have after a long time? You were trying to find the current?
I thought I had to find like the I2 here. But, yep.
That's fine.
So I found the total current. So that would help, right?
You found the current right after the switch is closed, right? I'm concerned here about the charge after a long time. So you need to find it after a long time.
So after a long time, it's gonna act differently.
Erase. Just put the erase marker.
It'd be like nothing.
Mm-hmm. That's open. Right.
And nothing. Then nothing is here.
Nothing's here, basically. You ignore
What
that.
does that mean?
That means
Because we have to find the charger too.
you need to find the charge out. To find the charge,
And it's
how can you find the charge on the capacitor?
yeah.
So
But-
you know this. You know that it's capacitance, right? Don't they tell you how much? What's the capacitance of
Yeah,
C2?
they do give
Yeah,
you
they give you the capacitance. So the only thing that you don't have is this.
the volt.
So you want to find the voltage at C2 after a long time.
If you're, this is like a battery, right? Or you assume it's just nothing because it's coming in and out.
It depends when. It can act like a wire, battery, or an open circuit. So the capacitor is basically two plates. A capacitor is basically two plates. Like in reality, it's just two plates together,
Yeah.
right?
The
When
very
you,
transfer.
the second you start charging it, it doesn't stop the current from flowing through it at all because it's not charged here or charged or not, and also not charged here. So current charges just starts to accumulate here, and charge starts to leave here, and that
Yeah.
keeps on happening exponentially until it becomes fully charged, or is it like this?
To the vault, right?
Yeah, exponentially either way. I know which one. But I mean, then when it's fully charged, it's actually like this. Yeah. When it's fully charged, current stops passing through it. That's when it acts like an open circuit. Current stops flowing through it. Now now it's fully charged, and the reason it's holding that charge is because there's a voltage from here to here due to this battery, right? It's creating a voltage difference between it. That's keeping the charge there. The charge wants to escape, but the voltage is too strong for it to escape. That's why when you disconnect this, all the charge escapes and flows the other way around. That's when it acts like a battery. After you disconnect.
When you disconnect this?
Yeah, when you disconnect the external battery, that's when it acts like a battery and starts to release charge.
So how could you find the charge on something that is like a battery?
How can you find the charge on something that's like a battery?
That looks like a battery. Like it's fully charged and then, oh, when you open.
It's not a battery. It's kind of like a battery, but
It's not.
this is its equation here. Q equals C.
When you
You have
unplug
to find
it.
the voltage of it. Find
Of
the charge
this?
Of the capacitor C2, yeah.
Okay, so you have to find this one first and then.
Yeah. You have to find how much voltage is in here. How do you want to do that? After a long time. This is the case after a long time. You just drew it. That's how it is. That's how it's going to be after a long time.
It should be the same. It should be, if you assume it's going this way.
Okay. So same here. There's a resistor here, so there's a voltage drop here.
No, I'm saying if you, can I assume it's coming this way?
What do you mean? What's coming that way? Voltage doesn't go. That's the current.
I'm saying about current again. Okay, so I have to do the voltage drop here, and then the same voltage would be coming here and here, and then the voltage drop here.
Yeah. The voltage drops again here, right?
Mm-hmm. And then
That's
there's
the
a
capacitor.
resistor again.
There's a resistor here. Is there a voltage drop across this resistor?
There. I'm thinking they should be, but there is a battery on top and in the bottom.
Not because of the battery. What's the voltage of a resistor?
IR.
IR. Is there current here?
No.
No.
So it's
0
voltage is
times
zero.
R.
Okay. 0 volts. So it'd be just that. Okay.
because it's an open circuit. There's some current.
Should I do the rest of that other homework too?
Hmm?
The other that one.
What about it?
The rest of the homework.
What about it?
Should I do it?
I prefer we do, yes. Preferably. Why didn't you do it?
I stayed up really late trying to figure out why this I2 and I3.
Why didn't you do it earlier?
Why didn't I?
Do it earlier.
I don't know. I came here. It took me a long time. Really?
Here's what you did wrong. Maybe there's other stuff not here, but so it's positive one. That's right. Substituting negative, right?
I think that's one. Oh, yeah. So that's it? 5.45.
That's the current. Oh no,
No.
that is, what's that?
This one is a current. The total current.
Oh, that's the current, okay.
Is it on?
Current is, let's see, that argument was made over 12 volts over 2.
Total charge.
42. Why is it 42? What's our equivalent? What's our equivalent?
Our equivalent? R1, R2.
R1, R2.
And this one, R1, R1 plus R2.
Right. Why is it 242?
If it is closed, these are gone.
Yeah,
These would act like nothing. This would go away.
This resistor has no effect. So it's just R1, R2. Yeah. Oh. Okay. Suck up my hand in the board. So you just found the wrong R equivalent. Just pay attention what you're ignoring, what you aren't.
If this is closed.
When this is closed,
This
at first, he's only going to ask, he's most likely
0
only going to
seconds.
ask you at 0 seconds and at infinity.
Okay.
So after a short time or after a long time. I mean immediately, which is, you want to say short time, or after a long time. Short time, which is immediately, what happens?
Short time. This would exist.
This would exist, yes. This is just a wire. It has no effect. It has no impedance. It's allowing current through it completely. So it's basically just a wire. So that's when you would do this. If he asked after a short time, and they asked after a long time, yes. If they asked after a short time, you would do it like that. And that would be the right current to flow through here.
In a long time, it acts as a battery where
After a long time,
you
yes.
ignore.
After a long time, there's two cases also. After a long time, it might be still charging or being discharged. After a long time, this is closed. This is nothing. It has already been charged.
It's still a wire.
It's not a wire. It's an open circuit. It's not allowing charge through it
Okay. So it would be like this, but
be
just
like
closed.
an open circuit. No, open. It's open.
Yeah, I mean like that, but this is still.
This is still closed. This is not affected by this. This is one circuit, and this is like just an extra branch that's disconnected from it. No currents flowing there. Nothing's happening there.
And when it's open, it's still the same thing.
And when you open this, these have charge in it. So when you open this entire circuit's gone, right? Because there's nothing here. Oh, why is this happening?
Is it because it had this?
No. Did I break something? Huh. Whatever. So when you open this, this is gone. This branch is gone. There's no current flowing through here. From here to here, there's no current. So you can ignore this entire thing. There's only this. That means there's a capacitor, a resistor, a resistor.
That's just it.
That's your circuit.
I did not know you would ignore this once you close it. I thought you considered it.
When you open it.
When you open it.
Yeah, when you open it, yeah. When something's open, it's gone. It's gone from the circuit.
Yeah.
It has no effect
Like,
on the
there's
current.
nothing.
There's nothing. From here to here. For current to flow, something has to be closed. Current can't flow through a line. It has to be closed. I think you did everything else right. Okay. This is correct based on the longness.
I think I flipped some numbers because I knew some signs were wrong.
Just to review it, review it step by step if you realize it's something wrong, because a lot can go wrong with these calculations.
I really suck at this class.
It's not easy.
That's what I got.
That makes sense. Well, this is calculated based on what you did. Yeah. That's what I know about calculations. I honestly don't. When I tell you, you ask me about something and I tell you something is right, I'm gonna say I mean something's right based on what you did. I don't know. You might make calculations.
The concept?
Yeah. I mean, I don't really care about calculator errors. That's fine. That happens. Professors shouldn't care too.
So how would we find the charge here if that is gone?
Okay.
Or just the resistor is gone?
No, basically the entire branch is gone. So basically there's nothing but, I mean, this is now like this. There is no wire here, right? So there is no current, right? There's no current flowing from here to here, but there's still a voltage. That's why there's a difference in current voltage. There's a voltage from here to here, though. That voltage is the same as here to here. Is there a voltage from here to here or not?
There's a voltage.
There is a voltage.
Would the voltage, like, what?
There's a voltage from here to here, right?
Mm-hmm.
And the voltage drop across a wire is, how much would the voltage decrease from here to here? Going from here to here. How much would it decrease? Huh?
It won't.
I'm what? I'm wrong?
No, the
I'm
voltage
asking.
won't. It won't.
It won't decrease.
It won't.
It won't. Right.
Right.
It won't. Sorry, I thought you said you're wrong. I'm not telling you something. Right. It won't decrease from here to here.
Yeah.
It won't decrease from here to here either. That tells you that the voltage here is the same as the voltage here. Right? So this is V1, that's V2, and V1 minus V2 is equal to 0, and V1 is equal to V2. Right? So voltage across here is the same as voltage across here. But pay attention, the voltage across here is not the same as voltage across here. There's a resistor here. There's a voltage drop.
So if you find the voltage here, and which is equal to that, would it differ from here to here too?
Yes, because
there's a battery. How would you?
There's a capacitor. Of course, the resistance has no effect, right? Because there's no voltage drop across here. So it's basically a coil. So voltage drops from here to here. And voltage drops from here.
Now, you find the voltage here, right?
Mm-hmm.
And then there is a battery. Would it be like the
Capacitor. Yeah. That's fine.
Is it a capacitor or you treat it as a battery?
This is a capacitor. I mean, always treat something as it is, a capacitor. But I mean, just if you want to think about it like simpler, I mean, right now it doesn't act as a battery, so it's not accurate to say. It still doesn't act as a battery. It still acts as an open circuit. But even an open circuit has a voltage. So if you connect a battery like this to this, there is a voltage across here.
Mm-hmm.
I mean, so there's going to be a voltage. There's a difference voltage from here to here. But that doesn't, I mean, current doesn't have to happen when there's a voltage.
Okay. So you treat it as a capacitor.
You treat it as a capacitor, as an open wire, a capacitor, exactly, yes. So you find the voltage of that capacitor. That's what we mean. All you need to do is find the voltage of this. When you find the voltage of this, you have that equation that gives you the charge. And you know, C1 and C2 are 40 and 80. 40 and 80, right? This is 40, and this is 80, I believe. Yeah.
Yeah, and you have the voltage, and you find the voltage difference, and then the voltage here, and you find it, okay. You have C, you have a V. How would you find another V difference?
How would you find another V difference?
I have to find the V first, but once you find the V2, yeah, once you know that, how would you find another V here? Or would it be the same V here and here?
It's called V equals, C equals Q over V, right? That means V equals Q over C. Okay. V equals Q over C, right?
What is Q over C?
Yeah. That means, okay, let's see how I'm going to do this.
Because we have, if we find V2, we have C.
Let's call this entire voltage V total. That's from here to here, all right? Let's call that V total. So that's the total voltage from here to here. That V total is going to be equal to V1, voltage of the first capacitor, V2, voltage of the second capacitor. Since V equals Q over C, it's Q1 over C1 over C2 is equal to...
What's C2 or Q2?
Huh?
Is that Q2 or C2?
That's opposite, right? That's Q2 over C2.
So you have to find Q1 too?
No, we don't. From this equation alone, this tells you that the voltage is inversely proportional to the capacitance. And it's linear. It's a linear relationship. So, if you know that the voltage across one capacitor is 2, and that capacitor has a capacitance of 4, right? The capacitor with C equals 4 and B equals 2. A capacitor with C equals 2 is going to have a voltage of okay.
Are you talking about the voltage again?
Another rate. These two capacitors are connected in series, right? Right? What do we know about two capacitors connected in series?
Inversely proportional. The total.
What is the same and what is different? What is?
Voltage is the same. Voltage is not the same.
Voltage is not the same.
It's voltage and current, right?
Charge.
Charge are the same.
Isn't it? Right?
Yeah.
Okay. That means the charge on this is the same as charge on this.
Mm-hmm. So you find...
You can also do it like you said, inversely proportional. You can find the equivalent capacitance.
That's what I would do.
Do it. Find the equivalent capacitance.
But I have to find the total V first. The V.
Yeah. It doesn't matter which one do you do first. Well, you're going to need that too.
Okay, this V is valid, right?
This is
V1.
V1 is equal to, yeah, okay.
And I used 12 times this, which was wrong, I think. So I have 12 times this would be the voltage across V1.
12 times that. Why 12?
The voltage? To find the voltage here.
Mm-hmm.
Don't I have to find the voltage here?
Yeah.
So to find this, I would take the voltage coming here times the current to find the voltage loss times this.
The resistance. Resistance. V equals IR. Voltage of the resistor is IR. The current times the resistance.
Isn't that what I said?
You said voltage.
To find the voltage.
To find the voltage, you said you multiply the voltage by the current. That's it. But yeah, okay. In context.
I'm
I just know you said it in context.
Okay.
Yeah.
So V1 would be, that's what I said. Okay.
V1 would be.
It's technically V total minus whatever V I get.
Exactly.
But.
Or you can also do it directly.
How do you do that?
Look at the resistor that's connected in parallel. This resistor. Isn't the voltage across this resistor the same as the voltage across here?
Yeah.
You can direct, and don't you know the current? Isn't the current that's flowing through this resistor the same as this? Because there's nothing here, right? And these are connected in series.
Oh, yeah.
Right? So I times R corrected. But yeah, do it that way. If you don't think about that, you could, there's like a million ways to do these circuit problems, so you don't have to do it in one specific way.
That's wrong. That's the I. Oh, never mind. Yeah, I have the wrong number.
Yeah, wrong number.
I have 20.
For what?
For.
How did that happen? Is that 0?
I got R. R times this.
0.09. Huh.
I get 20.
That's a big current. Wait. This is the one from the previous one, isn't it?
No.
This is V over 132.
That's just the resistor, the total. This and that.
Yeah, that's 242.
Yeah.
It's R1 plus R2 equal to. Oh. Wait.
Wait, what did you do?
Why'd you do them in parallel?
What did I?
Actually, both of them are wrong. But yeah, you did them in parallel.
Both of them are wrong?
Yeah, but well, hold on. You did them in parallel. Why'd you do them in... Did you do them in parallel? How'd you get 132?
This, I would just take this plus that.
Plus
That's
that,
what
yeah.
I meant to do.
Okay. Yeah, just do that. Erase that. Actually, erase this also so it doesn't stay here.
This one?
Yeah.
Getting confused
That's
and
fine.
confused even more. Sometimes.
So R. And that's this.
Yeah?
Yeah, that's also R equivalent.
Oh God. 1,000. Can I say I EQ? Or no?
Sure. Yes. That's fine. You can call it whatever you want. You can call it I name it. One cares about variable names.
I got 8.
Got it? Okay, that makes sense.
Two release. Total charge on both of them would be the same as the charge on this and that. You're looking at me like a creep.
Whispering.
What?
Nothing.
Okay.
Why do you look at me after every step?
I don't know. I feel like I'm doing everything wrong.
I'm gonna tell you if you're doing something wrong.
Okay. Alright. So this times 2, 26.6. I feel really dumb. I'm not a dumb person. But this class is making me look really, really dumb, and I hate it. I hate it. And I'm gonna hate physics forever.
No, that's fine.
Is it cool?
These were given in microfarads, so that should be microcoulomb. Multiplied by them, yeah.
Took me almost an hour to do one problem. That's awful.
The more it takes you, the less it takes you later on.
Capacitors, when they're connected.
Okay.
What?
What else? Isn't that the answer?
I don't know.
Oh, isn't that what they want?
What?
Isn't that what they want?
I don't want to write it. I want to do it again.
Okay.
I feel like I'm not going to get it right again.
Alright. Do you want to send it? To yourself?
Mm-mm.
No?
Mm.
You don't want it? Okay.
Would you explain one problem and then I'll
Sure.
leave
Sure.
the previous homework? So first one. Hmm?
This one?
Yeah. I think I tried to do it in my notes. I tried multiple times. I couldn't get it right.
Okay. And circuit containing resistors, the equal resistance with equal resistance R. Okay. The current I2 in terms of resistance.
Can I send this to myself?
What?
Can I send this one to myself?
Yeah. File, export as PDF. Just that?
Yeah. And maybe if we do the same one.
Okay.
Or if you do it all together.
We can, yeah. Okay. Yeah. I'll send them afterwards then. I'll send them afterwards. Okay. Yeah, here.
I want to pull it out.
Here, this is.
Should I draw it?
Yeah. All the same resistance. All of them are R. In terms of current, I want this is R2. Okay, And that's I1 here. And you need to find I2 in terms of I1.
In terms of I1?
In terms of I1.
Is it like you do everything you have to do, but just keeping this in terms of I1? Yeah. I2 in terms of I1. I1 is total current.
I1 is the total current, right?
So in that case, it would be the same. This one is. Oh wait, it was different. Say 3. Can you? I1 plus I2 plus I3. And you have to find total resistance to find the total current.
You can.
Is that what you have to do?
Yeah, you can do that. You have to find I2 in terms of I1 in any way you want. You can use Kirchhoff, you can do it by inspection, you can simplify it with, do it how you want to do it.
Can you assume this I is the same as that one?
It is, isn't it? By assumption, it is.
Would that help you solve this?
Maybe, depending on the way you want to solve it.
I don't want to do the hard way, and that's usually how I
But
go.
it should be going the same way.
Using this, would that make it easier or harder? Is it a professional way?
It depends on what you want to do. There's no such thing as a professional way.
Alright. I would solve for the total current.
Okay.
Total R.
Okay. Do that.
And then find total. Can I do that?
Sure. I'm not, you know that each R is the same. It's the same as the same as the same as the same as this.
Can I assume it's 1?
That, well, preferably not.
Okay.
Preferably
So
just keep it in terms of R, preferably, yes.
Okay, so how do you go up?
Down.
This part is equals to 2R.
Mm-hmm.
And then this side is 2R times R, or 3R.
Mm-hmm.
And you have, I'm going to do this and then that. Just need to use cross R. This would be second. And then the parallel one says you have this to that.
The current doesn't branch. This is the same as putting it in a straight line. You can stretch this, like if it's a wire, you can
It is
stretch
easy.
it. Yeah, it's easy.
So plus 1, 3, 8R, 3. And do you have the voltage?
They call it EMF, so epsilon. Or usually, you can just call it V. You don't have numbers at all.
Okay, I find this I. V, 3, 8, 4, R. So that's I. Is the same?
Hmm?
It's same.
What?
I1 is same here and here and here.
No, I want branches here.
Oh, no, it's not. Okay.
You already hooked, I want to collect you. Concentrate.
So that's I1.
Mm-hmm.
How would I find I? Oh, I could find I2 with this being just 2R. This one is 2R times I or times B. Let me think.
Remember how you used to do the capacitor problems? When you have a big circuit, and you make it into one single bit, capacitor or whatever, you find the charge on that, and that expands slowly, depending on parallel and series. Okay, oh, this is the same because they're in parallel. Oh, this is the same because they're in series. Same thing works for resistors. That's what you do.
I was just gonna do like the sum of these two.
Okay, the
and
sum of these two.
I on that one. But the sum of that one.
Sum of these two, that's going to be 2R, right?
Mm.
The current here is not the same as the current here. The voltage here is the same as the voltage here. So that means if you find the voltage across here, which is the voltage of...
So do you have to find the voltage?
You don't have to do this entire thing, right? but look.
You're making me think.
No, it's not about this. It's not about this. You might not think about the way that I'm going to show you how to do it.
Okay.
But I mean... Isn't that the same? If you simplify this into one resistor,
Yeah.
you get that same thing. What's the value of this resistor?
What's the value of that? 1, 2, 3. What is 1, 2, 3? Is it just this one?
Right, 2 over 3R.
So 2/3 R.
If you can find the voltage here, you know that that's the same as here.
So the voltage would be this, like this times that.
Right. Which is the current times the resistance.
Just 2 for 1/4 R.
Right.
So
1/4 B.
1/4 R.
Multiply it again.
You know?
R's cancel out. Yeah. I told you, I said 1/4 B.
Okay.
Oh. Because it's R times 1 over R.
Yeah. So these 1/4.
1/4 B. Just to keep track of the variables.
Okay.
Because you're going to need them now, soon.
So the voltage set was the voltage here.
That's the voltage. Yeah.
So the voltage,
Which is the same as something here.
the voltage
Yeah.
is the same here and here.
Because this originally came from this.
So 1/2 of that voltage would be the voltage here.
Yes, I can see that. Yes.
1/2 of this one would be the voltage at
Mhm.
this point.
Mhm.
Would be 1/8.
The voltage between these ones.
Yeah.
Yeah.
So 1/8
1/8 would be that voltage, the voltage of R
of our
to whatever they called it, right?
Mhm. So 1/8 times this would be just, wait, it has to be in terms of I1.
Has to be in terms of I1. Write it down. What's the voltage? What's the voltage of this in terms? What's the voltage of that? You said 1/8, right?
Mm-hmm. V is 1/8.
8. Okay.
And
So that.
I, should I try to solve right?
Yeah.
2 is R times V. I'm sorry, that's not true. Is that true?
No.
That's not true.
No, it's not.
V is like R. Of V over R, that is just R. How would you get that into Python? So this is really bad looking.
No, I just don't like the fractions and fractions. That's I2, that's I1. And they want you to.
So V is 8/3 I1 R. Simplifies that I2 1/3. Seriously. That's it. One. Okay. What was the easy way?
I1 though.
Oh. What's the easy? You made me do this.
Yeah.
Okay.
Okay. You know that this current is I1, right?
Mm-hmm.
I1 branches into here and here.
Mm-hmm.
The resistance over here is twice as much as the resistance of this. E equals IR.
The resistance
The
here
resistance here is twice as much as the
one.
resistance of this.
Mm-hmm.
So this branches into here and here.
Mm-hmm.
Since the resistance is twice as much
As the resistance.
as there, the current is going to be half as much as the current here.
Okay. I don't really understand this part. Like why is
Right.
half?
Because V equals IR,
Mm-hmm.
right? That means I equals V over R.
So
If the
either
resistance
2R
doubles,
or V half.
I would be half. So the resistance doubles, I should be half.
Yeah.
So this is half of this.
Mm-hmm.
That means if you have a share of 3,
Excuse me.
it's fine. If you have a share of 3, this is going to be a third, this is going to be 2/3. Because this has to be half of this. But
It's that easy. You made me spend 20 minutes on this. Okay. Got it.
You want to send it? You want me to send it?
Yeah. I don't want to do it again.
Okay. I'm going to send them individually, though, because this one is really ugly. Because it's all over itself.
Because you have the old problem there. That's the first problem.
And right next to each other. All right. So,
Thank you for your help.
no problem.
I tried reading the Business for Engineers.
Yeah?
It's confusing.
Is it? Which part of it?
Confusing.
Which part of it?
This part. Where
Oh.
where